Hello, Earth Science students. This is Dr. Hurt. We're going to be doing your 9th lecture today on weathering. This is going to be about how rocks break down. A lot of people might think superficially that weathering has to do with the weather. It doesn't have to do with the weather at all. It has to do with, I guess you could say, weather's effect on the rocks, but it has to do with how rocks break down and ultimately form sediment. Last time we talked about sedimentary rocks. I mentioned how we're going to be talking more about weathering the next lecture, so this is it. We're talking about how sediments form and how those sedimentary rocks ultimately form from the sediments and the breakdown of other rocks, okay? So you're going to see we have two types of weathering. We have what's called physical weathering. Sometimes another word for this is mechanical. So mechanical weathering. And we have chemical weathering. Okay, so you're going to see that physical weathering is where there is no, it's doing that annoying thing. There is no change to the composition. Gosh, I hate it when it does that. It's very annoying. Just like deletes my word that I made for some reason. Well, it doesn't matter. Chemical weathering is when there is a change. So this changes the chemical composition. Okay? So it changes the chemical composition. Here there's no change to the chemical composition. Just to give you some examples of really dramatic weathering environments, weathering might sound kind of like a boring subject, but it really creates some of the most beautiful and dramatic landscapes in the world. So Halong Bay in Vietnam, this is a really dramatic example of what's called karst weathering. So these really steep-sided hills, it's all from the weathering of limestone. Same thing, this is the weathering of limestone. This is what's called the stone forest. I'm not going to put this video on, but this is a really cute video of lemurs that live in the stone forest in Madagascar. It's pretty cute. But anyway, yeah, last time I tried to show this and it got tagged on YouTube for copyright infringement, so I'm not going to do that this time. But also the Badlands in South Dakota. It's another example of differential weathering. These little mountains have a funny name. They're called hoodoos. I don't know where they get that name, but they're these little highly weathered hills in South Dakota. So pretty cool. Bryce Canyon National Park, I showed this before in the beginning of the Sedimentary Rocks lecture. These are all examples of differential weathering. Arches National Park's example of weathering features. So also Monument Valley National Park in Arizona. These are all different weathering features. Some of these things represent the necks of volcanoes. So at one time there was maybe a volcano here like that, and this was like the magma feeder tube that was coming up to allow the eruption. But over time it just got eroded away, and all you get left is this kind of like magmatic neck. I don't know if this is how these specifically formed. In fact, I don't think I don't think that they did, because you can see the sedimentary rocks. But there are structures like this that are left from the erosion of volcanoes, and they leave just the necks of the magma feeder tube to the vent. So anyway, all those structures that are pretty cool landscapes were all just created by different kinds of weathering, and you can see weird pedestal rocks like this. It looks like someone almost put the rock on top of there purposely, but it's all just created by kind of what's called differential weathering and different types of weathering. So we're going to talk about all those different kinds of weathering today. Weathering, what happens if you leave a car out and exposed to the elements for a long time. This nice car probably was, only 50 or 60 years ago, really looked good. And, you can see what it looks like now. And it didn't really take very long, right? Maybe only a few decades, and this car looks like, well, you could see what it looks like. But the same thing is happening to the rocks, right? So rocks are not exposed for just 100 years. They're exposed for millions of years, sometimes billions of years. and it really takes a toll on them. Whole mountain ranges. I mean, it's mind-boggling to think of this stuff, but like whole mountain ranges have been reduced to just ashes, to dust from weathering, just from the passage of time. These like near eternity like stretches of time that happen in geology. And it takes mountains like take the Appalachians. The Appalachians, there's still mountains there, but those used to be the size of the Himalayas. I mean, you used to think of like Mount Everest, but what are they now? They're pretty modestly sized mountains now. They're just a few thousand feet high, and used to be probably 29,000 feet high, 30,000 feet high, but now they're pretty modestly sized. What happened? It's the effect of time, weathering, and erosion has beaten those mountains down to the ground. So rocks are broken up, pulverized, destroyed by the effects of the weather, exposure to the elements, the wind, the rain, the ice, the snow, the sleet, all that stuff weathers the rocks and causes them to break into pieces. So you can see the bedrock here. This is the bedrock that's still, like attached to the crust, right? So this is still part of the crust. But it's slowly been weathered away, and you can see these big, what are called talus slopes. This is called talus slopes. It's a good word to know. Some of these words, it's like I don't ask about them on the lecture assignment. Like I don't ask you to like define what a talus slope is, but I will refer to it. Like on the test, I might talk about a talus slope, and if you don't know what it is, that's a problem. So, I just want to kind of remind you that when you do the lecture assignments, it's a good idea to take notes on top of doing the lecture assignments. So there's information there that's in the lectures that's important, but I don't necessarily ask a question specifically about it. So just want to remind you of that. But this is something you definitely want to know, and I can almost guarantee you it'll be both on the on the midterm and the final, and that is you got to know what weathering is. And very simply, it says a pretty simple definition. Weathering is just any process that breaks up, crumbles, destroys solid rock, okay? And it turns the rock into loose pieces. And those loose pieces here are called sediment, okay? And sediment, you probably remember the last lecture, comes in different sizes. Could be clay or sand or silt or boulders or cobbles or pebbles, but it takes solid rock like this and turns it into sediment, okay? So we have two types of weathering, okay? We have chemical weathering and we have mechanical weathering, aka physical weathering, okay? So you can call it by either name. And don't get confused, because like sometimes I'll ask about stuff like this, like mechanical weathering. What are the two types of weathering? And people will say physical and mechanical. So physical and mechanical is just the same, different words for the same thing. So mechanical weathering, the difference between them, again, this is something I often ask on both the midterm and the final. What's the difference between mechanical weathering and chemical weathering? Mechanical weathering is just anything that breaks up the rock without changing its chemical composition, okay? So like if you were to take a hammer and just break a rock, that would be mechanical weathering. On the other hand, if you were to take some acid or something and throw it on a rock and let it sizzle and break down the rock chemically, that would be chemical weathering. Okay, so that's the breakdown of rock by chemical alteration. So chemical weathering changes the chemistry of the rock. It changes the elements and molecules that are in the rock. Okay, so we're going to learn about all the different. Most of this lecture are just going to be about different weathering processes. And a very common question I ask you on the test, I'm sure it will show up either on the midterm and or the final, is like, what are some examples of chemical weathering? What are some examples of physical weathering? And describe those things. Give me a description of what that process actually entails. So these are different processes, okay? So let's talk about different kinds of weathering, chemical weathering first. So we'll look at chemical weathering. I'm going to talk about three kinds of chemical weathering examples. So First, I'm going to talk about how granite weathers. You know, granite, and this applies to like rocks like diorite as well. It's just kind of how crustal rocks weather, I should really say, weathering of the crust. There's a real important process here that kind of goes along with this called hydrolysis. So you should know that term. Okay, hydrolysis. We're going to talk about the role of carbonic acid, and we're going to talk about the role of oxidation oxygen. So carbonic acid, by the way, I'm going to say this a few times in this lecture, but basically you have CO2 in the atmosphere. That CO2 will dissolve. Okay, here's my water. Okay, this is supposed to be water. The CO2 molecule will dissolve into the water, and it will become what's called carbonic acid. So that carbonic acid is HCO3. Okay. So, and that's HCO3, whoops, -1. It's an ion. I'm trying to get rid of this. Let me see. No, that's not the right button. Eraser. There we go. Okay. So you'll make this carbonic acid. Okay, and that carbonic acid is responsible for breaking down a lot of rocks. Okay, so you got to know this whole process. It's really important. I want you all to know this. This whole process of CO2 from the atmosphere, carbon dioxide from the atmosphere, dissolving into some water. Could be ocean water. Could be the natural, spring water. Could be groundwater, rainwater, whatever it is, and it creates carbonic acid and acidifies the water. And then oxidation. So let's talk about these different things. Let's look a little bit about how granite weathers. So just kind of generally, what you'll see is that weathering in general is going to round things out. So it's going to knock off sharp corners and sharp edges, and you're going to get this process of rounding of the rocks. So in a lot of different places you'll go and you'll find boulders, rocks, granite that kind of look like this, and they sometimes just look like spheres like this, like somebody's actually carved these out, and no one's carved them out. It's just it's called spheroidal weathering. So this is a very common texture that develops when granite weathers. So weathering processes tend to round off the sharp edges of granite. Okay, so and that's because weathering is constantly acting upon the surface of the rocks, and it's going to tend to reduce the surface area and minimize the surface area on a particular clast. Okay, so it's going to round things out. And a lot of the specific process that's taking place is hydrolysis. We're going to talk about hydrolysis a little bit later. So this is more spheroidal weathering in granite. Okay, so the hydrolysis of granite. Hydrolysis is a process that takes place when slightly acidic rainwater dissolves some of the minerals like feldspar, transforms them into clay minerals. Granite is a very hard and resistant rock, but becomes weakened and disintegrated when feldspars are broken down by hydrolysis, and quartz crystals remain loose and the debris unaffected. So basically what I said before is that CO2 in the atmosphere dissolves into, let me get some blue color here, and here's my water. Maybe it's rainwater even, but it dissolves into the water and it becomes this hydrogen. Okay, it becomes this carbonic acid. Okay, so what you're going to see is feldspar. Let me get a yellow so you can see this better. So feldspar is going to, it's a very common constituent of a lot of crustal rocks, right? So it's a very, very common mineral. It's the most common mineral of the crust. That's why I asked you this a few times. What's the most common mineral of the crust? It's feldspar, right? So feldspar in the rocks plus this slightly acidic water is going to give you kaolinite, which is a clay mineral. You probably remember, or hopefully you remember, when we talked about minerals, I made you know. I hate it when it does that. I don't know how to turn that off. Isn't that annoying? Well, whatever. Gosh, I can't make it stop doing that. I'm gonna write it really fast. There we go. Okay, clay minerals. Then plus silica and plus potassium bicarbonate. So what you end up with after feldspar and water, you end up with clay minerals plus silica which is like quartz, and then plus potassium bicarbonate, which is going to be dissolved. You can see this aqueous sign, the AQ stands for aqueous. This is going to be dissolved in the water, okay? So what you're going to end up with is that you see how this guy is holding this like bunch of kind of crumbled up granite. So it's actually kind of cool. Once granite weathers in this way, it's really easy to crumble apart because all the feldspars turn to this very weak clay. And it's very easy to crumble it, and you could even do it with your hands, you know. So, right, another kind of more. This is more like in-depth chemistry. You don't need to know it to this degree, like the specific reactions, but you should know feldspar plus water gives you clay minerals plus quartz and this potassium bicarbonate that's dissolved in the water. You should know it to that extent. But this is 2 KAlSi3O8. This is feldspar. Okay. Oh, it says it up here. Okay, so this is feldspar plus the carbonic acid in the water, right? So slightly acidic water gives you the kaolinite plus the potassium bicarbonate plus the silica SiO2, which I hope you remember that SiO2 is quartz, right? So this is just quartz. Okay, so that's how weathering of granite occurs by hydrolysis. So that's one way that water can weather rocks. And I think I have a question there, like what are some ways that water weathers rocks? So that's one way, is hydrolysis. Okay, oxygen in water can also react to form oxides of iron. So this is called oxidation. Now, you know, this is another thing, is that oxygen, O2. Okay, so O2 it can go into water. So here's my water again. It can go into the water and dissolve. Okay, so you have dissolved oxygen in the water. So this is, by the way, like this is what like fish breathe. You know, like you know that in H2O, there's oxygen in water in the sense of like H2O molecules contain oxygen. Okay, fish don't break apart H2O to get that oxygen. They are breathing the oxygen that is dissolved in the water. So my point is to you is that there is a lot of oxygen. There's a lot of different gases, but oxygen also it's dissolved in the water. So that O2 in the water is very reactive. It's kind of funny. It's more reactive than oxygen in the atmosphere. I don't exactly understand that. I think it has to do with some in-depth chemistry things that I don't want to get into, called chelation. But suffice to say, I'm sure you all know that if you leave like an iron piece of like an iron tool or iron something out in a dry, like in the house, you know, it's not going to rust. But as soon as you leave it out in the rain and it gets wet, then it will start to rust. Okay, so it's the combination of water, the O2 and the water, that is very reactive with iron, and then you start getting rusting. So, you know, iron is a very common component in a lot of different rocks, and what can happen is the iron in those rocks can react with the oxygen in the water and basically rust it, and it can create Fe2O3, hematite, which is rust. That's literally what rust is. So whenever you see rust, it is a mineral called hematite that is Fe2O3. It's iron oxide. Okay, so whenever you see like red beds, red rocks, you see red soils, you know, you should see the reddish color here. That's all hematite. It's just iron oxide. So all these rocks, you see beautiful red sandstones in Arizona, for example. It's all just iron oxide weathering of the rocks. Okay, highly leached soils, like soils that have become like very red in color. They're known as, by the way, laterites. They're actually a really good source of iron ore. They are highly leached by the rainwater, and they contain abundant hematite. They're mostly, at this point, hematite. So it's just like I mentioned before in the previous lecture, hematite's a really tough mineral, and it doesn't get broken down. And it's like the last thing, after a lot of weathering has occurred, it's like the last thing to be left over. So these soils have been leached and weathered so much that they're almost just hematite left over. So we talked about now oxidation. We talked about hydrolysis and weathering of granite. The last chemical weathering process I want to talk about here is carbonation. So carbonation think about, if you have a nice, right, fizzy drink here, you have your Coca-Cola or whatever, it's, as you know, it's carbonated, right? So when you open up that Coca-Cola, you'll see all these little bubbles start to rise out of the Coca-Cola, right? Same thing with a beer too, right? If you have a beer, here's your nice frosty mug of beer. Okay, there's the handle. It's supposed to be the handle to your mug. And you know that a good beer, you know that a good beer is going to have what's called a head on it, right? So it's going to have like that froth that comes up on the top, right? So there's the head on your beer, or even root beer is going to have that head of froth on top, right? And there it goes dribbling down the side. So what is that? Well, it's all CO2, carbon dioxide. Well, in some cases it's CO2. In some cases it's nitrogen. There's some beers that are somehow they're filled with nitrogen gas. I think Guinness is actually in that category. But in any case, what you need to know is that head is created by CO2 in the Coca-Cola. It's created by CO2 that is dissolved into that liquid. So this is a thing that's kind of weird for us to think about. Like, we think of like sugar and salt and solids being dissolved in water or a fluid, but gas does it too, big time. So CO2, oxygen, all the different gases dissolve in the water to different varying degrees. Nitrogen dissolves into the water at different varying degrees. So the thing is, though, is that when CO2 dissolves into something, it becomes acidic. So it makes it slightly acidic because it forms that HCO3 carbonic acid. Okay. So CO2 will dissolve in atmospheric water vapor, forming carbonic acid. Okay, so it'll dissolve into the rainwater. It'll dissolve into whatever. I mean, at the ocean, into the lakes, streams, whatever. That carbonic acid in the water will become a weak acid that slowly dissolves minerals in rocks, especially limestone. Now, I hope that I've impressed upon you at this point, like how, limestone is made of calcite, right? And calcite, calcium carbonate, calcite, is very susceptible to weathering. Do you remember where we looked at all these pictures and things where you drop acid onto the calcite and it eats it away? It causes it to bubble. I asked about that a couple times. I think I asked like 2 times in the mineral lecture assignment, like, what mineral fizzes with acid, reacts with acid? So the answer is calcite, right? So calcite's really susceptible to acid in the rainwater, okay? And it'll eat it away. So you can see this pitting in the limestone is created by the acidic water eating it away. So rainwater is always a little bit acidic. Any natural water that you encounter, it's gonna usually be a little bit acidic, and it's gonna be a little bit acidic because we have this process of CO2 dissolving into the water. Not a lot, but it's going to be a little bit acidic. So acid in the water eating out the limestone is what creates caves and what creates sinkholes and caverns, and that's all known as karst weathering. Okay, so karst weathering is just the process of breaking down limestone landscapes and creating this very unique sort of weathering. So caverns and caves are a part of the weathering of limestone. It's a very common topographic feature when you weather limestone. Karst is a very common feature when you weather limestone landscapes. Here are Bull Shoals Caverns. This is in Arkansas, but just giving you, again, examples of the kinds of things that happen when you weather limestone. Okay, so all these caverns, everything you're seeing is travertine, limestone, calcium carbonate. It's all from dissolution of limestone by the acidic water. So, there's all sorts of things. So let me see what maybe this dark blue would be good. So when you have the limestone kind of low to the ground, okay, so this is stage 1, and there's water seeping into the limestone here. You can see the water seeping in. It's going to start dissolving and creating caves. And there's going to be a cave formed right at the water table. Okay, see the water table. See how like the rocks under here are below the water saturation limit. We're going to get more into like water tables in the next few lectures, but you're going to start developing caves here. Now, if due to tectonics, this area raises up, or perhaps the water table lowers, you're going to get these caves exposed to the land. And sometimes these caves will collapse at the surface. You'll form sinkholes and things like that. So there's all sorts of interesting things like disappearing rivers and caverns and sinkholes, and there are all sorts of things, travertines, stalagmites, stalactites, those are all things that form from karst environments when you have limestone being dissolved by water. So all these sinkholes and things that you see here, it's all when you have limestone underneath. Limestone's a very weak rock. It dissolves and weathers very easily, and it forms these sinkholes. So places like Florida that are all limestone, Tennessee, Kentucky has a lot of limestone. Of course, there's limestone in Texas as well, but a lot of those places have a lot of sinkholes because of their limestone underneath. So the limestone has formed caves, the water's dissolved it, and they collapse. So this is a very famous example of this was in Bowling Green, Kentucky. There's the National Corvette Museum, which is kind of crazy because I used to travel a lot. My mom lives in Tennessee, and when I was in grad school in Michigan, I used to drive by this Corvette Museum like every time I'd go to visit my mom. And it was nuts. I mean, one time I went by there and it had literally gotten like swallowed up by a sinkhole, and I think like something like 30 Corvettes got swallowed up. And you can watch the video. They actually have it on captured on their video security footage, so you can watch it actually happen right there. I'm not going to play it for you, but yeah, sinkholes happen. Here's just one. China is also got a lot of limestone, and so the kind of like dubious construction methods combined with that limestone, there's a lot of Chinese videos of sinkholes forming. So here's another one. There are like millions of them, but yeah, that happens. And then this guy, I guess, didn't see the sinkhole and fell into it. So I don't know. Hopefully he's okay. Actually, as scary as these things are, very few people actually die from sinkholes. So, but anyway, that's chemical weathering, and now we're going to just move on here to physical weathering. So physical weathering is when rocks break down over time due to mechanical, physical processes that do not change their chemistry. So we're going to talk about a few of these. Jointing. Well, let me change my color here. Jointing, frost wedging, root wedging, salt wedging, and thermal expansion. Some of these are I'm just going to cover really fast. So whenever you have weathering, especially mechanical weathering, you create these talus slopes at the bottom of cliffs and bottom of bedrock. So, by the way, I kind of tried to impress this upon you in the last lecture, but usually the places that are weathering and eroding are high places, high topography areas, mountains, and cliffs and things like that. We don't have so much of this in a place like Corpus Christi, weathering and erosion, because a lot of the rocks are buried underneath layers of sediment and layers of mud. Okay, so we just don't get as much weathering and erosion here in Corpus Christi, Texas. If we were in the mountains, we would see more things like this, right? So, but anyway, let's talk about all these types of weathering. So the first one I mentioned is exfoliation and jointing. So when you have for example, a granite that was formed in a magma chamber. Okay, so imagine here's the surface of the land. Maybe I'll switch to that color. And here's your grassy surface of the land, right? And there's a little tree. And oh gosh, it's doing that thing. I hate that. Okay, there's my tree. And then you have a magma chamber form underneath, right? So you have your magma chamber. Okay. magma. I don't know why it likes to erase my stuff. I really don't. Okay. Whatever. I'm not going to argue with it anymore. But anyway, this is supposed to be my magma chamber. So it's going to, over time it's hot, but eventually, it starts to cool. Okay. So it's cooling, cooling, cooling. And it's going to solidify. And, over time, there's going to be weathering. And this stuff, here comes my weathering. It's going to weather away that land surface. And eventually, the new land surface is going to be down here. And this magma chamber is going to be exposed. Okay, so now here's my tree. Here's my house. And we have a magma chamber exposed. So, when it was buried deep below the earth, there was very high pressure. But now that it has been exposed at the surface, the pressure is low. So now it's low pressure, low P. Okay? So what happens is that when you depressurize these solid rock magma chambers, they get these pressure cracks form as the magma chamber depressurizes. It expands because it's expanding. Okay, as you take the pressure off of the rock, it expands, and as it expands, it starts to kind of exfoliate and slake off the skin on. Because you could imagine if maybe it's kind of gross image to imagine, but you could imagine that if all of a sudden, or maybe this is a good analogy. Think of like a snake or a reptile growing, or a crab growing, and that they shed their skins because their skins get too tight, right? So they slake off their skin, and as they grow and expand. So the same thing is kind of happening with the rocks now that they're exposed at the surface. So at pressure, they were kind of compressed and contracted, but then when they got to the surface, they expanded and grew, and they slaked off that outer layer of skin, if you will. So this is called exfoliation. And this is a type of jointing. Okay, jointing is any process that kind of like cracks the rock due to like tectonic stresses. Another example so you can get this exfoliation jointing, which is called sheeting. Which is from the reduction of pressure. You can also, from the cooling of magma, you can also get a type of jointing from as like the magma cools and contracts. So, you can think of that, it's kind of the opposite process. So you can imagine that when you have a body of magma form, a body of especially basalt, it's really hot and fluffy. But as it cools, it contracts. And as it contracts, it pulls and squeezes together, and it forms these cracks, vertical cracks and columns. Okay, so this is really famous. You find this kind of texture all over the world. These are called columnar joints, and they form in basalt when a basalt, like basically a puddle of basalt, a pool of basalt cools and contracts, and it forms these joints that look all the world like somebody made this, right? It looks like somebody carved out these little hexagonal pieces, but they didn't. This is 100% natural. It's called columnar jointing. And like I said, Devil's Tower National Monument, Wyoming has this. There's all sorts of places you find these columnar joints. It's actually pretty common. So exfoliation, creates this sheeting. Deep rocks under pressure, slowly uncovered by erosion. The overlying layers are eroded away. The pressure is released near the surface, and the rock layers peel off along cracks, kind of like an onion skin, to produce these large dome-like features in the landscape. So exfoliation produces domes. So for example, the most famous example of this is Yosemite's Half Dome, which is an exfoliation dome. So there it goes. There's a really stunning picture of Yosemite and Half Dome at Yosemite. So it's really, really cool landscape there. It's another I love Half Dome, so I put a lot of pictures of it. That Yosemite's a wonderful, awesome place. I all hope you get a chance to visit it sometime there in Central California. This is a cool video I'm going to play for you really quick. It's just some guy was standing here and literally caught on camera he's standing on like a hunk of granite and literally caught on camera exfoliation cracks forming. So you can see it's pretty terrifying. So you can see all of a sudden he sees the cracks there forming. You can see the popping and the smoke that kind of came, and then boom, you can see it all cracked at one time. So it's pretty neat. It'll play again if you wanted to see it, but you can see little cracks forming. And then he pans out, and you see all of a sudden all these cracks forming. So anyway, that's happening, before your eyes. So another type of mechanical weathering that happens is when rocks are either pulled apart or compressed, and you form joints. So this can happen just due to tectonics, like plate tectonics, like one plate of rocks is smashing into another one and compressing, or the plate is pulling apart. So these are very common processes. Anywhere where you get earthquakes, the rocks are moving and shifting. They're either being compressed or they're being pulled apart. So when you get compression, you get joints that form like this, that you see how they're forming at these 90-degree angles. Okay, so if you compress a rock, I looked really hard for a video showing, because I've seen videos before where they take like a rock and they put it in a vise, like a big vise, and just start pressing it, and you can actually see these cracks start to form at these angles. So this is very common to get cracks and joints from compression like this. That's called jointing. When you pull rocks apart, and there's what's called tensile stress, where they're being pulled apart, you get these parallel cracks that are perpendicular to the tensile stress. Whereas when you compress, you get these sets of cracks. You see how there's like two sets of cracks, one in this direction, one in that direction, right? One in this direction, one in that direction, that are forming kind of not exactly perpendicular. I think they're forming at like 60 to 120 degree angles to each other, that are forming again at kind of tangentially to the direction of the compressional stress. Okay, so that's a very common way of getting cracks in rocks, and it's kind of interesting because when you see compressional stresses like this, you will think that they got cuts, like somebody went and like professionally cut them, but they didn't. They form these really straight, even sets of cracks. So it's pretty interesting. So once cracks appear, it's really easy for water to get in there, and if you're in a place where there's freezing, the water can get into the cracks, and it can start to, gosh, isn't that annoying? I don't know why it keeps disappearing like that. It's this whole thing, yeah. I don't know how to turn that off. I really tried hard to turn this off on this new pen I bought, but I can't figure it out. Anyway, the water will seep into these cracks, and if you're in a place where there's freeze and thaw cycles, it'll freeze, and as you know, when water freezes, it expands. So if you've ever put like glass jars, like glass mason jars or anything like that, into the freezer, you could actually do this at home if you have some glass jars you don't want anymore. You can fill them up with water, put the lid on like that, and it'll crack the jars when you freeze it. It's very strong. So, whenever there's a freeze coming through, like there's just one now coming through Corpus Christi, Texas, as I speak this. It's not common here, but it does happen. Like sometimes people say like you have to leave your water on a little bit at night because it might burst the pipes and things like that. And that does happen. So, freezing water is very, very, very powerful. It can crack and destroy rocks, pipes, jars, anything easily. The same kind of process happens with salt. So salt can come and get into little cracks of rocks, and the salt crystals grow, and they can break apart the rocks that way. It forms this very characteristic honeycomb pattern. And you'll see this very, in coastal areas. I haven't found anywhere in Corpus Christi where I found this, but I'm sure if I looked around, I could find some of this honeycomb pattern of weathering. And that happens again with salt wedging. So again, salt mixes, salt water gets into the cracks, it evaporates, and the salt crystals precipitate, and they expand and break the rock apart. Thermal expansion can also break rocks as well. So like if you live in an area where you're going through these cycles of like heating and cooling, and maybe there's, some places, it's not so much Corpus Christi, but like if you're in the high desert or something like that, it can be really cold at night and really hot during the day. And when you have those cycles of like hot and cold, the rapid expansion and contraction of the surface of the rock causes cracks to form and propagate. So that's another way that you can weather rock. So here's some more pictures. I wanted to show you some pictures of like jointing, and you can see like these perfect, almost like perfect, square rectangular shapes are cut out of the rock, and it almost looks like somebody came here and like started like cutting with a saw or something to make tile or something like that. But it's not. That's really like from the jointing, natural jointing from compressional stress. And it's kind of cool because now when you go, if you guys ever see this somewhere, you automatically know that this formed in an area. This is a reaction to compressional stresses. So you know that this area was under some kind of compressional stress, right? So there was some kind of plate tectonics or something happening that was squeezing this area to form rocks like this. I want to shift gears a little bit, talk a little bit about differential weathering. So differential weathering is when you have weak rock layers that weather out more quickly than strong ones. So differential weathering is kind of cool because it produces a lot of these interesting environments, like the Arches National Park, and it creates these different structures, dramatic structures that are standing up tall among other places. So all this stuff is created by differential weathering. So arches, for example, you'll have these deep cracks. So these might be joints, for instance. So it start off as joints. And then erosion gets into those cracks and enlarges the cracks. So you end up with these things that are like fins. So you can call these fins here. And then if you have frost and thaw, it will flake off the porous sandstone and eventually cut through some of the fins. So if you have a different rock type kind of on top that's more resistant, or maybe like, for example, less porous, then the rock type that's underneath, if it's more porous and weaker, it'll get eaten out, but the rock on top will remain. So, eventually these things are destined to collapse, but for the time being, they're kind of cool. You also see differential weathering in these things called pedestal stones. So, what happens is you get in places, especially like sandy deserts, you might have a layer of rock that's sitting on top of a weaker layer. So this stuff is weak. This is strong. And what happens is that the wind is blowing. The wind is blowing and it's picking up the sand, and the sand is kind of abrading the surface here. So it's kind of, think of like a sandblaster. It's a way of like, stripping paint and things off of furniture, off of your house or whatever. So the sandblaster abrades this weak rock and it weathers it until you have this funny looking little pedestal. And you have this big, strong rock on top that is out of the way of the abrasion of the sand, and also stronger on top of it, so it doesn't get eroded. So eventually, you end up with these pedestal rocks that look pretty cool. Getting close to the end here, I just want to talk about biological weathering. So life in all its different forms can weather the rocks as well. Some of the most obvious things that I'm sure you all know about are plant roots. And I'm sure that you've all seen this happen before. Plants will send their roots into the sidewalk and will tear up the sidewalks, right? So walking around the suburbs in Corpus Christi, I'm sure you see this all the time. The sidewalks are just torn to pieces by the roots of plants. So plants do the same things to rocks, not just sidewalks. It can do the same thing to rocks as well. Also, all these guys, fungi, lichens, bacteria, all these guys will actually go and secrete organic acids to weather the rocks and extract some nutrients from them. So, over time, they might seem like kind of small organisms, but over time and in combination with each other, they can really do a lot of damage to the rocks. So they are kind of, in a way, almost eating the rocks away. Because they are trying to extract things like potassium and phosphorus and necessary nutrients from those rocks. So, over time, I just want to say that, weathering is what's called a positive feedback process. Positive feedback process. So that means that the weathering, it's a snowball effect. So positive feedback processes are processes that accelerate with time. So, you know, when a rock is broken into pieces, whoa, I need a dark color here. There we go. When a rock is broken into pieces, it creates more surface area. And that creates, in turn, more surface area for weathering processes to work on. And that, in turn, creates more surface areas for weathering processes to work on. So the process accelerates as more cracks are generated. So, again, that's called a positive feedback process. Now, this last part, I just kind of want to put this out here and have you guys think through this about what effect climate might have on weathering. So, like, if you were to imagine, for example, a desert climate, what kind of weathering processes do you think would be common here? So, you know, you're not going to have, there are certain things you're not going to have, like you're not going to have frost wedging, right? That's not going to be a problem. But something that could be big here is thermal expansion, right? Because you have these hot, very, you know, you probably from being in the deserts, if you guys have ever camped in the desert or anything like that, you probably know that it can get really hot in the day, but really cold at night. So thermal expansion could be a thing here. Also, just the normal processes that don't really care about climate, such as jointing. You know, that could be a common, because that's mostly based on tectonics. It's kind of indifferent to what the climate is like. But things that you won't find here are, for example, frost wedging. You won't find a lot of biologic activity. Also, there's very little water. So you saw all the ways that water erodes rocks, right? Hydrolysis, oxidation, carbonation. Those things aren't going to happen here so much. So you can see that there's really not too many processes that weather rocks in the desert. And that's why, for example, I think of Davis-Monthan Air Force Base in Tucson, Arizona. They have what's called the Boneyard out there, where they store all the old Air Force airplanes. And they put them out there for a very good reason. It's because there's not a lot of weathering processes to destroy those planes. So that's why they keep their official boneyard, aircraft boneyard out there. Now, on the other extreme, think of a tropical environment. You know, you have everything under the sun going on here because there's lots of water and there's lots of life. So you have all the like biological, right? Biological. Oh my gosh, that is so frustrating. I don't know why it does that. Biological weathering. You have all of the different types of hydrolysis. Everything associated with water, because there's a lot of water in these sorts of environments. So you have carbonation. You have, what's the other one? Oxidation. And you have things like, thermal expansion. You have also, if it happens to be close to the coast, you can have salt wedging. All these different things. So, and of course, you have all the things that are indifferent to climate, like jointing as well. Okay, so all those things happen in those kinds of tropical environments. Probably immediately looking at this picture of a polar climate, you would expect, frost wedging. You would expect, jointing. And also, to a lesser effect, if you have any water, liquid water, you can get all the normal liquid water processes like hydrolysis. You can get carbonation, and you can get oxidation. So, but frost wedging is going to be a big one, right? Frost wedging is going to be big here. So I just want you guys to kind of think through what kind of processes you're going to get dominating in certain climates. Okay, so it's kind of intuitive in a way. You can kind of think through it and figure it out. So that's all I have for you today. Hope you enjoyed the lecture, and I will be available to answer any questions as always. And hope you do ask questions, because we're getting closer and closer to midterm day, and as I've kind of warned you before, the midterm is difficult. So you want to learn this stuff. And if there's anything that's difficult for you, you don't understand, please reach out to me and let me help you. So anyway, that's all I'm going to say here. And I hope you have a good week and a good weekend. And I will talk to you next time.